This presentation will show the basics of modeling heat pipes using Thermal Desktop's FloCAD module. These tools are intended for the thermal engineer who needs to simulate a system containing one or more heat pipes, usually to verify their operation under various usage scenarios. Sorry to start out on a negative note, but the topic of heat pipe modeling is loaded with spurious details and dead ends, and I want to avoid those traps. The key here is that the tools I'll be presenting are intended for the heat pipe user, not the heat pipe designer. And I know this distinction isn't always perfect, since designers will need to investigate at least a little bit about what their heat pipes will be subjected to. For example, it isn't always possible to design using steady-state extremes, especially for variable conductance heat pipes. But for an engineer integrating the heat pipe into their system, the heat pipe user in other words, that perspective is different. They need tools to verify that the designer has done a good job, that thermal gradients are as promised, that there are no transient conditions under which problems arise, and that the heat pipe hasn't been over-designed either. It turns out they don't need to know the gory details of what is happening inside the pipe in order to do this integration and verification task. We have separate tools applicable to the heat pipe designer, but the heat pipe user need only know whether or not a heat pipe has hit a limit or how close they have come. They don't need to know what the specific cause of that limit was, nor what happens when that limit was exceeded. After all, if a limit is exceeded, or if it comes uncomfortably close to being exceeded, then they need to call the designer for a new pipe. Another misconception is that the heat pipe acts just like a bar of very conductive material. First, you can't assign a number like 1,000 times copper to a heat pipe, since the conductance or resistance is largely independent of length. Trying to use a highly conductive bar gives you the wrong behavior. Similarly, you can't just replace a heat pipe with a large Cinda conductor, since that provides no information regarding operational limits. Also, that approach doesn't distinguish between vaporization and condensation resistances. So, how should you model heat pipes from a user's perspective? The user needs to know how the pipe behaves. What temperatures will equipment, plates, and radiators arrive at when they're adjacent to this heat pipe, and how much margin is available compared to the transport limits. The traditional approach for such modeling is to use a fan-shaped conductor network, with the energy from the evaporator and condenser regions flowing through a single point, a temperature representing saturation. That saturation temperature is modeled by a single arithmetic or massless vapor node. CR Tech didn't invent this technique, it's been around for decades. We've merely made it convenient and accessible within a geometry modeling environment. The network diagram on this page is applicable when there is no gas present, and we'll talk more about gas later. It also shows just a 1D slice, and again, we'll defer the talk about dimensions until later. For now, the key is to see that each axial segment is directly tied to a central node representing an average. The fact that all of these segments are strongly connected to the same temperature internally, irrespective of their position along the pipe, shows you why a conductive bar approach is no good. A distinction is made between evaporating and condensing film coefficients. But in reality, those differences are not that great, because whichever direction the heat is heading, those coefficients are usually large enough that they don't cause much of a temperature drop compared to that of wall material and wet wick structure. Phase change is not the bottleneck, in other words. A key concept in heat pipe sizing is the power length product, QL effective. Each cross-sectional design can be characterized by a power length product at a given temperature, adverse tilt, and for a given working fluid. In the simplified case with constant temperature zones, the effective length is the sum of half the evaporator length plus the whole length of any adiabatic section plus half the length of the condenser. For example, if a 2-meter long pipe had a 1-meter long evaporator and a 1-meter long condenser but no adiabatic section, then the effective length would be half the total, or 1 meter. If that same pipe could transport 500 watts, then its QL effective would be 500 times 1 meter, or 500 watt meters. To understand this figure of merit, note that if the same pipe cross-section or wick design needed to transport twice the power of 1,000 watts, it should only be half as long, such that 1,000 times 1/2 meter is still 500 watt meters. The Thermal Desktop heat pipe tools don't assume any fixed lengths for evaporating, condensing, or adiabatic zones. Instead, these tools integrate the QL product along the length of the pipe so that there can be multiple evaporator or condenser sections. The total QL product is reported back to the user as a CINDFluent register so that they can compare with a vendor-provided number to see how close the heat pipe is coming to its limits. The QL product does not cover all transport limits. It excludes boiling limits, for example, which are rarely the main driver in typical applications. Similarly, the single saturation node method of modeling does not cover all situations, such as the startup of liquid metal heat pipes. I'll talk more about those limitations later. But the single node method and the QL method do cover most room temperature heat pipe applications from the perspective of the heat pipe user, as was the intent. I promised I'd return to the topic of NCGs, or non-condensable gases. Gases usually appear in pipes either purposely in the case of VCHPs, where they're added for control reasons, or accidentally in the case of CCHPs, where they're considered a performance problem related to either initial quality or lifetime limiting degradation. In the case of VCHPs, the amount of gas is known and is a key design parameter along with the reservoir volume and the temperature control scheme. For CCHPs, the amount of gas must be guessed, perhaps as needed to explain test data. In both cases, the gas moves to the cold part of the pipe and blocks condensation there. This gas is modeled in FloCAD as a flat front, as if a cylinder had been inserted inside the pipe, blocking off portions of it. The program solves iteratively for the current gas position, summing up the amount of gas in each section according to the partial pressure, and blocking each section's heat transfer accordingly. Since Cinda nodes are used to represent the internal details of the pipe and not fluid control volumes, any fluid motion is instantaneous. The hydraulic solution is quasi-steady state, even in a transient. The position of the gas front is available as a Cindafluent register for post-processing and other uses. Let's take a look at what happens when gas is added to a constant conductance heat pipe. The figure at the left shows an unblocked pipe with no gas. As gas is added, more and more of the condenser is blocked, and the temperature of the evaporator rises to compensate. In other words, the resistance of the heat pipe is increased. This temperature and the length of the block section are shown in the plot at the left. In a variable conductance heat pipe, gas is added purposely to vary the resistance of the heat pipe, usually to prevent the evaporator from getting too cold. In the hot case, however, the gas needs to get out of the way, so a reservoir is provided to absorb that extra gas. The temperature of this reservoir is usually regulated to control the temperature of the evaporator or the temperature of whatever the pipe is attached to and is cooling. A VCHP introduces thermal gradients into the condenser, and this means that the condenser must be subdivided as needed to capture these gradients. Also, since the reservoir's temperature is critical to the operation of the pipe, its attachments, environments, and control system need to be carefully modeled. Again, it should be noted that the thermal desktop tools are not intended to design the VCHP. The reservoir volume and gas charge are considered input parameters given by the heat pipe designer. However, because of the complexities of a VCHP, a major reason for using these simulation tools is to discover cases where the reservoir volume and gas charge are inadequate, and to see if the heater control algorithm needs to be adjusted in order to better handle the real conditions that the pipe will experience. So some degree of iteration between design and design verification is to be expected. I also promised to return to the topic of multiple dimensions. The model I showed earlier was one-dimensional. Each axial segment was represented by one thermal node and one temperature. That's equivalent to having no circumferential gradients, and that's often a good assumption with heat pipes because they're such good isothermalizers, not only along their length but also around the periphery. But if you have a saddle attached to the pipe as shown here, or you need to include the effects of uneven heating, or if you have a heat pipe that's bonded inside a honeycomb panel such that it touches two phase sheets that are at different temperatures, then you need more dimensions. It's easy enough to extend the central saturation node idea to multiple dimensions, but not as easy to extend the power length product concept, QL effective, nor to handle complex shaped gas fronts. So even in a 2D pipe, both of those remain 1D concepts. In other words, the QL effective product is integrated along the length of the pipe. It takes contributions from each circumferential segment along the way, but since it's only measured axially, the FloCAD base tool won't predict a transport limit from one side of the pipe to the other, just from one axial location to another. Now that's not an issue for tube-shaped traditional heat pipes, but it does complicate the estimation of limits for vapor chamber fins, which can otherwise be modeled as 2D heat pipes using FloCAD. FloCAD builds the thermal network representing the heat pipe and automatically invokes the required Cinda modules, whether 1D or 2D. This allows you to integrate the pipe with complex thermal geometry and boundary conditions, and to connect heat pipes to fluid loops and to other heat pipes as well. In the bottom two graphics, you can see the before and after effects of having added a set of 5 interconnected heat pipes to isothermalize a base plate. The design consists of 3 lateral pipes and 2 header pipes. The heat pipes in this case are actually inside the honeycomb panel, but they've been made visible for post-processing. In Thermal Desktop, heat pipes are a special case of FloCAD pipes, which are usually used to represent the fluid flowing in a duct. Once the heat pipe option is chosen, the Heat Pipe Data tab becomes active as shown. One option available is a fixed conductance heat pipe, which is also known as a constant conductance pipe. You can define the wall material, the wall shape and dimensions, and the coefficients for vaporization and condensation. You can also add gas to the system, in which case you need to define both the working fluid and the gas species. If you chose the VCHP or variable conductance option, you will also be prompted to input the reservoir volume and to point to a node that will represent the reservoir's temperature. Unlike CCHPs, VCHPs are directional. The reservoirs are assumed to exist near the beginning of the FloCAD pipe, which is assumed to be the condenser or cold end. But it's easy enough to reverse the pipe if you happen to have drawn it in the wrong direction. I'll show you some of these operations in a moment. There's no standard shape for a heat pipe. They can be formed or bent into all sorts of different shapes. Even their cross-sections are not always circular, although they may not be as fanciful as the one shown here. The point of this artwork is to demonstrate that both the centerline and the cross-section can be arbitrary. In FloCAD, you can sweep any cross-section along any centerline. Note that the cross-section you define is not the actual cross-section of the heat pipe, since all the details of the wick structure and the grooves aren't needed. Instead, these cross-sections just define the outer boundaries of the pipe as needed to attach to other objects within the model. If you're importing CAD drawings of a pipe, you may find the import and simplification features of CRTech SpaceClaim to be useful. That tool has an option called beam extraction that can generate centerlines and cross-sections from complex extrusions. I'll show you a demonstration of the FloCAD model building features in a moment. But first I wanted to show you an example of a racetrack-shaped pair of heat pipes used to isothermalize a heated plate. This illustrates how a traditional heat pipe network can take on added value when integrated into a tool that includes contact conductance, radiation, and so forth. I'm now in the Thermal Desktop environment, and I'm going to demonstrate a very simple model of a heat pipe. I've got a disk up in the upper left-hand corner that's hot, and a heat pipe coming down to a plate, rectangular plate at the bottom that's cool, and the heat pipe transporting the heat between them. If I go ahead and delete it, you'll see that the center line is left here, and that's an AutoCAD line that was used to construct the heat pipe, and I'll show you how we can recreate that too. So I'm going to go ahead and delete that and go back, in fact, to the input mode, and you'll see the plate and the disk now. And since I'm going to use just a simple circular pipe, I'm going to show you that it could have been a little bit more complicated if I defined an AutoCAD polyline, possibly with a few arcs in it, come the other way, and maybe terminate in a straight line. So this could have been my center line. I can then define a cross-section to extrude through that line. So to demonstrate that, I'm just going to come through and put in a pentagon. I don't have to line it up. FloCAD is going to take that and put it at the end of this center line and extrude it through. So now if I come through and define this to be a FloCAD pipe, it'll first ask me to select the center line, and then it'll ask me to select the cross-sectional shape. And if I just hit return at that point, it would have been circular. And to make things a little bit more visible, I'm just going to put in about cross-section of 40. Or excuse me, resolution of 40, and you'll see that it extruded along that warped center line. It extruded the pentagon, and that could have been a pipe carrying fluid, or it could have been a heat pipe. In this case, it's going to be a heat pipe. But that's actually not the heat pipe I wanted to build, so I'm going to go ahead and just delete that. You'll see the original cross-section here, and you'll see the copy of that FloCAD put at the end of the line in order to be able to extrude it along. And you can control twists and warps and how that's extruded through too. But what I want to do right now is demonstrate the heat pipe option, so I'm going to come back through and define another line. This time I'm just going to make it a straight line. I'm going to come down along the plate and up through the center of the disk, and I have my construction line now. If this had been a VCHP, I should have been careful to start that operation at the cold end, so that's where the reservoir would be placed. This is not going to be VCHP, so I don't have to worry about that now. I'm going to go ahead and make it a pipe again. This time I'm going to create a heat pipe. I'm going to again put in a subdivision so that we can see what's happening along the pipe. And I'm going to now go to the Heat Pipe Data tab, which has been activated by having selected this as a heat pipe. I'm going to leave it as a fixed conductance heat pipe for now, It's got a little bit of a large diameter, so I want to cut that back down again. And otherwise, I'm going to define a cross-sectional area. I could have also done it as a thickness. The unit of this model is in centimeters, so I'm going to define the cross-sectional area of the heat pipe to be 0.3 centimeters squared. Sometimes the heat pipes have complex cross-sections and you just want an effective mass per unit length or area instead of defining a cylindrical pipe wall thickness sort of arrangement as you would in a normal pipe. And so when I accept that, I have a heat pipe that isn't connected to anything yet. So if I were to run this, I'd have a hot disk and a cold plate and a heat pipe somewhere in between. So this is not a complete model yet. I need to contact the pipe to the disk and to the plate. So if I create a contactor, I'm going to go from the pipe to the disk and to the plate. And you'll see that shown here that my from objects for the contactor was a pipe, and I'm going from a disk to the plate. The contact conductance, I'm just going to use a value of 1 here, but I want it to be along the edge of the pipe, so I want it to be in units of watt per centimeter of length rather than an aerial as you would with a face where it's watts per centimeter squared, which would be appropriate if I were contacting on one side of the heat pipe, for example, but I just want to go along the center line and define it to be a conductance per unit length. And so I need to come back to my pipe here and change it to be along the pipe length for the conductivity. And I'm also going to reduce the tolerance here down to 0.5 centimeters, and the reason is I'm being kind of lazy. I basically have a cylinder that's cutting right through the disc, it's cutting right through the plate. I'm not bothering to offset it just for demonstration purposes. And I also didn't bother to do anything about this section of pipe that's really not touching anything. So I'm going to let the contactor do the work for me and just taper off any contact anytime the pipe can't reach any object that it was assigned to. But that's enough to be able to run the model. If I do make a run, it's going to warn me that I have duplicate node IDs. The reason is because I did not bother to set vapor IDs for the saturation node or make anything else unique. I don't really care what they're numbered, so I'm just going to accept whatever Cinda assigns. And so you can see I've got the results here of conduction through the disc to the pipe, down the pipe, and to the plate. And you'll see my results. If I go down to the end of my run, you'll see a couple of registers were created by Thermal Desktop down here. The gas position register for that pipe and the power length product for that pipe. This 430 is the QL effective that I was talking about earlier. That's 400 watts centimeters, since the units of this particular model are watts and centimeters. So that would be about, say, 20 watts of heat transported over 20 centimeters. To make things a little bit more interesting, I'm going to come back and add a little bit of gas to this pipe. So if I come and edit my pipe and go to the heat pipe tab, I'm going to change it to be a fixed conductance heat pipe or constant conductance, same thing, with gas. When I select that, you'll see that the working fluid and the gas property tabs became active. I'm actually going to turn the working fluid into ammonia here. I'll go ahead and let the gas be air, even though that's probably not realistic. It would probably be hydrogen in a real case. And I'm going to say that there's 0.1 grams or 0.001 kilograms of gas because it really doesn't take much to block off the pipe. When I accept that and rerun the case, you'll see that there's gas blockage now has occurred in the condenser. So this gradient that appeared here on the right hand side is caused by the gas that's over at this far end. But I'd like to know how much gas there was. And you can see too that the temperatures have gotten a little bit hotter up here since the active length of the condenser has been decreased. So if I come over to the output again and now look at the two registers that I had listed, you'll see that the power through the pipe has actually dropped, or the power length product. And the reason is it's transporting the same amount of heat but over a shorter distance. And you'll also see that the gas position is no longer 0. It's now showing that the gas is about 9.3 centimeters from the end. So that's the position of the flat front that's blocking off the condenser. You'll see that that's true from the temperature gradients as well, that it's somewhere about here is the gas position. So that demonstrates how easy it is to create a pipe, connect it, and to add gas to the pipe in order to be able to make a run. The FloCAD heat pipe utilities are a great help for system integrators who need to verify the operation of their vehicle or product. But it's also important to know what the current limitations are, and this topic is covered in the next two slides. First, While FloCAD pipe wall options are not limited, when the heat pipe option is chosen, only 1D and 2D finite difference objects may be used as walls. In other words, unlike any other pipe wall option, a heat pipe wall cannot be a finite element mesh. As a side note, if you're new to Thermal Desktop, you should know that this restriction applies just to the heat pipe wall. Any other part of the model can be finite element, lump parameter, and so forth. Part of the reason for this restriction is that the actual geometry of pipes can be very complicated, whereas the traditional heat pipe analysis method eliminates the need for this complexity by using effective film coefficients and an effective vapor core diameter. If the internal details of the heat pipe can be simplified, the Cinefluent utilities could be generalized in future versions to handle finite element heat pipe walls. Another limitation I'd like to point out is specific to vapor chamber fins, which I've mentioned before. This limitation is the lack of a more complex 2D gas front and power length calculation. Otherwise, the program is applicable to vapor chamber fins. Probably the first thing that people new to heat pipes learn is a set of common transport limits such as sonic, viscous, boiling, and so forth. So they're usually a little surprised to see it all condensed into a single power length product, QL effective, in FloCAD, since that's often focused on the capillary limit. This simplified treatment of transport limits could be revisited in the future. For example, if the boiling limit were more commonly encountered, a different check would be added since that limit scales with heat flux rather than total power transported. Also, if analyzing liquid metal heat pipes and low temperature water pipes became more common, we could extend the modeling capabilities to include simulation past the sonic and viscous limits, since those are often encountered during normal startup. But what I think is really needed before those features is more specific data from the heat pipe manufacturers, including QL effective as a function of saturation temperature and adverse tilt. If that data were more readily available, it would make sense to expand FloCAD to help with the calculation of adverse tilt, since it already understands the rest of the geometry. For now, the takeaway from these last two slides is that the program is intended to help with the most common needs, but it doesn't do everything. There are rare application-specific needs that could be addressed by future code expansions if the trade-off between cost and benefit were to change. The primary purpose of this presentation is to cover fixed and variable conductance heat pipes. But there's another class of devices that's being used more and more, loop heat pipes, or LHPs. It's too much to try to describe loop heat pipes here, so I just wanted to make two key points. First, they're very different from traditional counterflow pipes, both in their design and analysis. The second point is that Thermal Desktop and FloCAD have the capability to design and simulate them as well. Because LHPs are so different, the modeling methods are not similar to what we've been discussing so far. So the bad news is that a simple sinter network is no longer appropriate. You require the more complete thermohydraulic solutions that are available in fluid submodels. The good news is that, in many ways, the options are much more extensive for LHPs because they're essentially a self-driven two-phase piping system, and those types of systems are one of the fortes of Cinefluent and Thermal Desktop. But it also means that there are more choices that must be made, especially with regard to specialized modeling requirements of the capillary evaporator pump and the compensation chamber, two devices which do not exist in a pump two-phase system. Many complex LHP systems have been successfully analyzed and references are available on our website. But you should be forewarned that successful LHP modeling requires more knowledge of what's going on inside the loop than is true for traditional heat pipes. For example, if you need to model both the first few minutes of a startup of an LHP and you need the fast-solving system-level response over the course of a few hours of operation, then you'll likely need two different models, one for each analysis requirement. One of the keys to successful LHP modeling is predicting the right amount of subcooling arriving back at the evaporator and compensation chamber assembly. That's good news, because Thermal Desktop and FloCAD have lots of tools that can be used to help predict this value. Also, the uncertainties in that prediction are comparatively low, since the condensers are often simple piping, however complex their plumbing arrangements and environments. In other words, LHP condenser modeling requires adequate resolution and attention to detail, but, unlike the rest of the loop, it doesn't require a lot of modeling finesse or specialized knowledge. Counterflow heat pipes, whether constant or variable conductance, and loop heat pipes can all be modeled using Thermal Desktop's FloCAD module. In the case of heat pipes, the modeling methods are based on time-honored techniques. In the case of LHPs, validated thermohydraulic solutions are applicable. But in both cases, these two-phase devices can be integrated into a system-level model that's perhaps based on a CAD drawing, or that includes finite element meshes, radiation, contact conductance, convection, and so forth. From the perspective of a system integrator, all the salient features of the heat pipe are tracked without getting lost in the details inside the pipe. Please feel free to contact us if you have any follow-up questions, and thanks for your time.